are slowly joining, sir. Some of them have already joined. So I welcome you again, sir, to this course, to this second session on fourth day. So
Yes.
thank you so much, sir, again for joining with us. And now you
Mhm.
can start.
So I have one question. So tomorrow, can we just swap so that we first do the tutorial on the Black-Scholes formula, and then I do the lecture on
Machine learning.
machine learning?
Yeah, sir. You can swap. No
Yeah,
problem.
yeah.
We
And so
will
this,
inform the participants in advance that you can do.
yeah, yeah. Okay, that's fine. Yeah,
Okay, sir.
because
Yeah.
because I have to leave early, so at 12:30 I have, so at my time. Yeah,
It's okay, sir. You
yeah.
please
Okay. Yeah,
take the tutorial first and
yeah.
then so what you want to do,
Machine
you want
learning.
to take the tutorial first and then you want to do the lecture.
Machine learning. As lecture, as last is a lecture on machine learning. Uh, so let me see.
Yeah, it's fine, sir. It's fine. I have seen.
Yeah,
So you
yeah,
can take from 8 to 10 the tutorial and then from 2:30, 11 to 1, 11 to 12:30 you can take the lecture. No
yeah,
problem.
yeah, yeah, yeah.
Yeah,
Okay.
yeah, yeah. Now you please proceed, sir. Thank you.
Okay. Morning, everybody. So yesterday we started with continuous time finance. Yeah? So we had as one example, just one example, the geometric Brownian motion to be the asset price. But basically, in the theory, you can take everything which can be a semi-martingale. ST can be semi-martingale. Any what's called semi-martingale. We might come back to this in the tutorial, semi-martingale. And I showed you some examples like solutions to stochastic differential equation and including jumps, Levy processes, and whatever. Okay, so we have an risk-free asset, ST0, and we have a risky asset. And this can also be a d-dimensional stochastic process. But let's keep it just simple. We have only one asset. But then we take a measurable process, which consists of two components, HT0, that's the investment in the riskless asset, so the bond, and HT, that's investment in the risky asset, ST. And that's called a trading strategy if we have the following property. The measurability is just defined below in the footnote what it means, but we have a more restrictive measurability assumption, namely that HT is adapted to the filtration FT. And so the second and third conditions is that more or less you can do integration, that you can integrate them. To get a finite integral, meaning HT0, the investment. That's also random. Basically, as we will see later again, we just have to define HT, and then we get a self-financing strategy, H bar. By defining HT0, by financing, lending money, or investing money in the money account. So these properties 2 and 3, they ensure that the integral processes exist. As we have defined SU0 to be e to the power RU, the integration with respect to S0 is pathwise, it's like usual analysis. It's in SU is a differentiable function. S0 of U is a differentiable function. Yeah. So we integrate by taking. We have the integral function EF equals F prime dt. Of course, the integration with respect to a real random function like SU is more difficult in this case because it solves the SU we had said is a geometric Brownian motion. So we have a drift. U SU du plus sigma SU du, where this is a Brownian motion. So this is what called the E2 integral or stochastic integral. So the definition of the stochastic integral, this can be found in many textbooks. And it can be and for this we need that HU is adapted. Now the textbook I usually recommend, it's a book by Karatsas and Shreve. Stochastic analysis is a book by Karatsas and Shreve. Brownian motion in stochastic calculus. That's not totally general because it only concerns continuous process. In this case, jump processes are not handled there. But it gives you most of the results we need for continuous Martingales or for Brownian motion you get in this textbook. Okay. And so it's bounded also in L2. And as in the discrete time and one period model HT is H bar, put it like this, it interpreted as a portfolio strategy. And then the value process, that's the value of your portfolio investing if you invest according to H bar is HT0 times ST0. That's the value you have in the banking account. The riskless asset plus HT times ST, that's the value of your investment in the risky. That's the value process like V. And the self-financing is if the strategy, the value of your strategy VT equals the initial investment plus the integrals 0t h0u d0u. That's as we had before, that just SU 0 du, because it's not stochastic, the riskless asset is not risky, not uncertain. The bank account plus the stochastic integral. And this will be motivated as in the case in discrete time. Now, this was our definition in discrete time of self-financing. If we have discrete time, we will time steps. And so we just write it in terms of increases. So the increase is just the increase of the riskless asset times the investment you have done at the beginning of the interval plus HT times your risky increase in the value of the risky asset. And so these are really differences. And if you let this time step tend to 0, so you get the self-financing condition we have seen before in terms of stochastic integrals. No, this is just a notation. DST does not exist. There's not a differential on ST. The only thing which exists is the integral. This exists. And so each time we write a differential equation in the context of stochastic analysis, what's really meant is the integral. So in analysis, it's an equivalent formulation because DST does exist, if ST is differentiable, but in stochastic analysis, it's just a notation, a short notation for the integral equation. And so if I give you more details on stochastic analysis, which we will have, I think, today, the second lecture today will give you more non-stochastic analysis. Okay. Now, if we take the discounted process, of course, then then we have directly the stochastic integral as we have also in discrete time. Then the discounted value process, we discount now. The first part disappears. So basically everything. That's what we would like to have because we want to figure out the hedging strategy HU to some extent. So this means each discounted value process with a self-financing strategy can be written as a stochastic integral with respect to your investment in the risky asset, HU, without 0 and without bar. That's the investment in the risky asset. So you see already, probably you're not so familiar with this, but this comes from stochastic analysis. You have the product rule, which is a basic rule in stochastic analysis. It's like the product rule of, again, I told you, this is only expressed shortcut, as shorthand for the integral equation. But if this would be a differential equation, that's just the product rule from differentiation. Differentiation with respect to t would give you, this one is a classical part, classical analysis. Where the covariation So the covariation, this gives you the additional feature of stochastic differential equation and stochastic analysis. So the covariation, the different definitions, and we might therefore have to learn so the product rule is kind of a first level E2 formula.
Sir,
Yeah.
why you not write in covariance term exponential minus RT?
Where? Here, VT, DE, this one?
No,
Of
sir,
course,
covariance.
you see at the end, so this one becomes this one. That's your question, yeah? That's the differential of E minus RT is minus RE to the power minus RT.
No, sir, no, sir. Covariation term.
Where?
Sir, in first line.
In first line here, DT, yeah? Here?
Here, where you take D of inner product.
Yeah?
Sir, last term, in first line, last term.
This one. Yeah?
Yes, sir.
Here.
Yes, sir.
Yeah? E to the power minus RT, yeah? Comma V
Yes, sir.
T. Yeah? You want me to write this one? So the definition, you have two functions. Yeah? Okay. Probably the covariation is defined for two functions. Yeah? You have a function T. Sorry. Sorry, it broke down. Okay, just a second. I have to reconnect again.
Yeah.
Join. My iPad was gone down. Okay. I have to share. Sorry. Share. This one. Okay, now you can see everything again, yeah? Okay.
Yes, sir. We can see now.
Yeah. So
yeah.
So I try to explain this bracket. Yeah, this bracket. So if you have a function,
Yes.
T goes to Ft, and you have a function T goes to Gt. Yeah, and both of them are not of finite variation. They are of quadratic variation. Quadratic variation means that this, I now define first quadratic variation. So quadratic variation That's you take f time t, f of t. And it's all these functions which are just continuous, they are not differentiable. What you do, the total variation you might remember from calculus means you take intervals here and take ft plus 1 minus ft I, take the absolute value, sum this, and then you get something finite if you're getting smaller and smaller here. Quadratic variation means you take these intervals, ti plus 1, but you square the difference. You take this ti smaller ti plus 1, the finite final, let's say up to time t. They are in what's called in this partition. This partition is just a subset. And you take limit tau n. So how small the distance is between time points ti, this tends to 0. Okay. And if you don't square here, the function, this weird function, this will be infinite. No? Because it's a local property. So these small differences, you have to take even smaller, namely you have to square them. If you just take the absolute value, these differences are too big so that they don't add up to a finite sum in the limit. So this means the small numbers, they're small but still big, you have to square to make them even smaller, then this becomes finite. Now, that's the properties of Brownian motion. It has a quadratic variation, meaning if you have a quadratic variation of a continuous function which is finite, then the total variation, or any, so this exponent is quite important. More or less for all these functions, you have just one exponent. For Martingales, you actually have two. If you don't have a and especially also for Brownian motion. So these are the path property of random paths. So they are, put it like this, they are very realistic functions. You see these functions everywhere in the nature. If you look, probably it's today in Germany it's sunny and cold. Probably in your country it's cloudy and hot. But if you look at the clouds, so the boundary of a cloud is a typical function which has no length. These functions I'm drawing all the time, they have no length in the sense length of total variation. Because how you measure length, you do exactly this one. I think if you don't do probability, you think mathematics is somehow gives you length of a curve, but we are concerned with curves which don't have a length, or put it other way, they don't have total variation. Because that's how you would measure it. You would take small intervals, make a linear approximation, and so on. Okay, that's quadratic variation. And the covariation, it's actually you take two of them. In each interval, you take the product of the increase. And then this is called f, g, t. That's why I've written here just the function e to the power minus r indicates, I mean, the function t goes to e to the power minus rt. And here there is also not argument that the function t goes to vt. Okay.
Okay.
So that's a basic ingredient of stochastic calculus on this level. Okay.
Yes.
Okay, and then so this is what's called the product rule or ethos formula from stochastic analysis. So then you see the quadratic variation. The quadratic variation disappears again, as the covariation disappears if one of them has finite variation. Because, as I said, there's only one exponent of a curve where you get finite value. If you are below this, it's also it's zero. If you are above this, it becomes infinite. For a continuous function, we will probably come back to this if we do some more stochastic analysis. But now first I want to go through the mathematical finance, and later we will get the details on the stochastic analysis. Yeah, you see this term with the argument. This one is again zero. The covariations, hence the total variation of this one is finite. Total variation. Well, because it's like a scalar product. Scalar products are by Cauchy-Schwarz are bounded by the product of the norms. That's a bilinear form. Even if it goes through the limit, you have all the properties here. So this one is bilinear form. And you also have this one is smaller than the norm of this. So that's a property of bilinear forms. And let's say if g of t equals e to the power minus rt, this one is here. Because you add up this small stuff and that's okay. Okay, this means we are now in the state where we have defined all the ingredients for for the most of the ingredients for the definition of the market, and define all the, let's say, basic elements of a market, the strategy, the underlying asset, and the strategy. Self-financing means it's a stochastic integral, and here you see the same argument. Once you started just with your investment in HT, investments in ST, meaning your HT, you get the HT0 by this formula, and this gives you then a self-financing strategy H star. In this sense, you can forget about the self-financing strategy, because investing the riskless asset will always gives you a self-financing strategy by this definition of HT0. You see, for this, you need to have this to be positive all the time. Okay. So this means in order to do a hedging, you just need H, and you automatically get an H bar. And self-financing definition looks the same. Arbitrage definition looks the same as in discrete time, or even in 2 times. You only need the first time point 0 and the last time point t, capital T. Okay. Now we need more mathematical background, meaning basics on stochastic calculus and diffusion model. So the first thing is I just explained you quadratic variation. And here in this preposition, in Levy's characterization of Brownian motion, you see right away why Brownian motion is so important. Also put it like this, so central. Because once you have now a Martingale, and you figured out a continuous Martingale, a continuous local Martingale starting in 0, and you see that the quadratic variation is actually T, meaning this quadratic variation so quadratic variation, do you have, let's say, 2 definitions of this? Of course, they are different in more general cases, but for continuous path, it's the same. You can say, okay, quadratic variation so quadratic variation of this process is defined as the only process that's the conceptual that this one is again a local Martingale. Or it's the same. So you have, like, let's say, the structural property that mt square, like squared, and then I subtract the quadratic variation, then I can get again a Martingale. And you construct, if you like, if you have a Martingale, a continuous Martingale, then you can construct this one by the limit I was just mentioning. You take the square increases, the square of the increments, and then you let tau n tend to infinity, tend to the mesh, how it's called, the mesh size tends to 0. So stochastic analysis in theory tells you if you have if M is a local Martingale, that M square is a sub-Martingale, and each sub-Martingale can be uniquely compensated by an increasing process. Now, this is, of course, increasing in T, because you add more. Variation increases over time. And so that if you subtract these compensator, then you get a martingale again, something stable again. This is an average increasing. And M is also increasing, so this compensates the sub-martingale. In order, you get a martingale again, which is constant, which is constant in expectation, which is stable. So a Brownian motion has this defined by its transition probabilities or distribution of the increments, can be characterized by a pathwise property, by a structured property. It's a martingale. Okay, martingale is to some extent also distributional, at least martingale conditions means it's the expectation MT given Fs, so the sigma S is smaller than T equals Ms. So on average it's stable. It says continuous path. It's continuous. And it has a property that this one is always T. Almost surely, it's enough. And probability is always almost surely. The probability must be 1. When it's a Brownian motion, then you actually know its law, its distribution. And this you prove by actually calculating the conditional, the given Fs, what's the increase, the distribution of the next increment. Increments. And you can show by just this property, by the martingale, you use it. This is a martingale, this one is a martingale. Actually, then you get what's called the exponential martingale. By Ito's formula, and by Ito's formula, you see, okay, this does not depend on, because here you see that's a conditional expectation, it's a random variable. This means it's actually independent. It does not depend on the value ms or what the path did before this time. It's just a deterministic function, and that's a Fourier transform of normal distribution. Okay. So it's basic. It's a basic property, fundamental property of Brownian motion. Its quadratic variation is T. In some sense, this means time is volatility. Somehow, if you have more volatility, more going up and down, then it's more volatile. It's just faster. Time goes faster, if you like. Only where the time is like the natural time, then it's Brownian motion. We come now, because we have learned, what we have learned in discrete time, discrete space, or finite time, we need an equivalent martingale measure. This means we have to work on measures, on distributions of stochastic processes. And that's the Girsanov transformation, which is also important in mathematical and stochastic analysis and in mathematical finance. This is all very important probability theory, independent of mathematical finance. You use it in any other application of probability. You use it like, if you do likelihood ratio tests, basically you also change measures. Or statistics, Pearson's lemma. Yeah? Nowadays, they are all formulated in terms, of course, of, if you like, densities, but densities is also a change of measure. Okay. So we start. Girsanov transformation tells you how to transform Brownian motion into other Brownian motions under different measures. Huh? It's unfortunate it's over 2 pages. Huh? Okay, so we take alpha t to be a bounded adapted process. Then we define a new process mt, which is what's called an exponential martingale. Bs is a Brownian motion, is a martingale under P. Then MT is also a martingale under P. So it's a generalization of our geometric Brownian motion. Before we are now doing, as I said, stochastic analysis, but if we go back to our Black-Scholes model, we had this one, dst equals mu let's see, we take mu equals 0. Let's say we start with 0 drift, and we know st, that our sigma equals sigma t minus sigma 1/2. That's asset price, Black-Scholes asset price with mu equals 0. Then it's also a martingale. And so your asset price looks like this. This means alpha s is always sigma. So we had done this case, we had already put it like this. The Black-Scholes word, it's a simple one, just formally it's the same. You get this exponential Brownian motion, which is also in general an exponential martingale. So we generalize this to like volatility being alpha t. So this means it solves the same linear stochastic equation, differential equation, or integral equation to be more exact. And so we get the exponential martingale out of this. So that's not the important part. The important part, if we have now a positive martingale, which actually starts at 1, so the expectation of MT is always 1. Especially the expectation at capital T is also 1. So it's a positive random variable which integral equals 1. Okay, we can use it as density. This we do in the next step. Because that's what we need. We have to find equivalent martingale measures. We now give us many, many, many equivalent measures by defining the densities in terms of this alpha. So to each adapted bounded process, you find a new probability measure Q, which has this MT as density. Huh? And then the important thing is then we get a new martingale or a new Brownian motion. This one is a new Brownian motion. We call it WT. Okay. Now we have a new measure. Now, under the new measure, BT is not a Brownian motion. But we have to add a drift. This one we call drift, huh? In order to get a Brownian motion.
Hello, sir.
Yeah.
How BT is not a Brownian motion?
Excuse me?
How BT is not a Brownian motion?
It is not a Brownian motion, huh? Because it has a drift. So the expectation under Q is the expectation of this one, for example. No? The Brownian motion is a property of a random function and the probability measure. So distributions are always distributions of random variable defined on a probability space where you have a probability measure usually called P. No? This makes stochastic analysis, but also mathematical finance. You have several measures. Namely, you want to go from your what's called the historical measure P to a pricing measure Q. And so it will always be the case, let's say you do a lot of statistics and you figure out your asset price is a Brownian motion with drift 20% or whatever. No? Your pricing measure will be different. No?
Sir,
Yes.
is this work like a scaling quantity?
It's not a scaling. No, it's not a scaling because it's a drift. It looks differently. I mean, you have these random functions. You have C, but the measure P gives different weights to different functions, to the same function. So it's always like it's to some extent it's a scaling, but because you can it's no, it's not a scaling in the sense that you I mean, it's a transformation, gives you you have a random transformation of BT. The transformation is you add a drift, then you get a Brownian motion again. Now this is your Brownian motion under P Brownian motion, and then this is your Q Brownian motion. It's always the relation between measure and functions. The probability, you measure the probabilities as functions falls in a certain set.
Okay. What about the quadratic variations and
Here's the quadratic variation. Yeah. So this means we have to prove WT is a martingale. The only property BT is not a martingale anymore under Q, because the quadratic variation will be the same. This doesn't change. This does not change quadratic variation. Because it has finite, the quadratic variation 0 because it has finite variation. This one does not change quadratic variation.
Okay.
Yeah. So that's how we see it. How we prove this. Quadratic variation remains the same. So WT will also have quadratic variation T. That's a pathwise property. And as long as the new measure has the same 0 sets, meaning also the same 1 sets, then the path property remains the same. So any property which holds with probability 1 under P will also hold with probability 1 under Q. That's it. Why you need equivalent measures. And on the other hand, we will see that WT is a martingale under Q, whereas B is a martingale under P. No, that's a martingale. This we prove here. W is a Q martingale. That's an important step. As you mentioned, as one in the audience mentioned, which I just know the letters of the names. So we have to use a property. Adaptness is clear, because adaptness is just has nothing to do with the probability measure. It's a question of the F, the filtration, which remains the same. So we only have to prove the martingale property. The martingale property we have to prove. That's one way to the easiest way. We have to prove that EQ WT equal WS. How do you calculate conditional expectation, or to prove that a random variable is a conditional expectation? We have conditional expectation. That's the random variable. That's equivalent. That EQ indicator AWT equals EQ indicator AWS for all A in Fs. We have to remember the definition of conditional expectation for this. Conditional expectation with respect to the sigma algebra is nothing else. You take a set from the sigma algebra and you say, okay, if you integrate the random variable, you can replace the random variable by its conditional expectation, then WS equals the conditional expectation. And this is what we do here. In this line, we say, okay, EQ indicator AWT equals, by definition, EQ, we do by integrating with respect to P, but then we have to multiply MT, that's the density, because MT is the density. Okay, but if we condition on Ft, we take that's a power law, and so Wt drops. If we take the condition, we can replace. We can take conditional expectation here. I mean, basically, we take conditional expectation. Expectation is the expectation of any conditional expectation. So we first write this like here. That's a power law. Expectation of conditional expectation is expectation. Then we figure out Wt and indicator of A is an Ft, so we can put it off here. But this one is a Martingale, so we can replace it by Mt. Then we take here the conditional expectation of all this given Fs. But E indicator of E is Fs measurement, we can take it out. Now we have proven before that Wt times Mt is actually also Martingale under PFS. So this is a Martingale Wt Martingale under P. So we take, it's a Martingale property. Then we go back from Ms to Mt again, because this is a Martingale Mt. And so we have Mt. We have figured out now our Ws, that's what we want to get out. And then we have Mt is again, Mt is a density of Q with respect to P. So this means that Wt is a Martingale under Q. And before, as I said, we have proven also by product rule. We had proven before that W times M is a Martingale under P. And here we have proven. And so I just showed step number 3 in order that you get motivated to rerun, to recall the defining properties of conditional expectation. Conditional expectation is not a computing device. Conditional expectation is a mathematical property, which is defined by this equation. You don't have to do calculus. You don't have to do computation. It's a structural property, which you can prove from the basics here. Now, for the other ones, you need again Ito formula. Here you don't. This is just conditional expectation, which one learns in probability 1 or 2. Now, so we have here one constraint, namely that alpha is bounded, but basically the only thing is we need that this Novikov condition is fulfilled, so that the local martingale, the exponential martingale is usually a local martingale, that you can prove that's actually a real martingale. Do you know what a local martingale is? Remember
No,
I
sir.
told you, yeah?
No, sir.
And Local martingale, by definition, with an increasing sequence of stopping times. So it's local. That's a localization sequence. Tn. Before we called it Tor-n. This was random once. Stopping times, these Tor-n's. Increasing sequence, so converging to the final time, such as the stopped process. Tor-n is a martingale. Yeah, this means they are martingale up to a certain time, but these times Tor-n they converge. That's why it's called local. It's not global, but it's local. Yeah, and so you have always to work with these limits. This means you have to do like integration, like monotone convergence, Lebesgue convergence, and all your favorite results on interchanging, integration, and limit, which you learned in measure theory, Lebesgue integration, or whatever, or analysis. Because you have to calculate these. All the proofs are then, okay, you just take here because they are all local, you have to stop them at tau n. Then you let all this in all this equation, you should let tend n to infinity, and that's possible if Novikov condition is true. And there are literature telling you, okay, crisis comes if your prices are only local martingales. And there is no sequence. They are not global martingales, they are not only local martingales. Because what we need at the end is martingale measures, not what's called local martingale. If your pricing measure only produces local martingales, then you are in trouble. Okay, this was a short citations, reminder, whatever, in order to get the tools to do the basic steps in continuous time finance. Namely, that's the Girsanov transformation in order to get a martingale measure. Okay, we have seen how to get a... Yes? Please?
Sir, I have a question.
Yes, please.
Sir, in Black-Scholes model, how will we use Girsanov theorem to go from real drift to risk-free drift?
Yes, so that's what we do now. So we apply now this Girsanov transformation to get our martingale measure, because we know, or we believe, whatever, that you have to price under the risk-neutral measure, and the risk-neutral measure makes a discounted process a martingale. This we will do now, arbitrage in the Black-Scholes model. Okay, so this was the definition. Black-Scholes model is ST equals MST dt plus sigma ST dBt. And all our favorite friends, the statistician, has estimated mu and sigma carefully, especially mu. I don't know, mu is very difficult to estimate anyway. Actually, sigma is easier to estimate with less data. By drawing inspiration from our different time settings, we want now to figure out a probability measure P star such as the discounted price process xt is a martingale under P star. And for this, we do Girsanov transformation. This means we transform not ST, we transform the BT. BT Brownian motion under P. No? Because I mean our ST is just a function. That's the driving stochastic process. If we properly change BT or change the measure such that BT looks different, it might be that XT becomes a martingale because XT is this one. Okay, we again apply product rule, and so our stochastic equation of the discounted process looks more or less the same as for ST. So that's our stochastic equation. dBT, especially if interest rate is 0, it's the same, because discounting has no effect. Okay, so that's the stochastic equation of our Black-Scholes model for the discounted asset price. That's not a martingale under P. Only if mu equals R. Because stochastic integrals are martingale. If this term is 0, then we have a martingale. So, but we have somehow figured out our BT, our BT, if we can also say BT, it's then WT minus alpha SDS. So we put it in XT, then obeys this equation. So we can rewrite this as we just add and subtract our we just put in BT because WT we just add, and then we subtract it again, but we just, I mean, XT dt plus, and we just rewrite this in terms of WT, but then we have, of course, sigma XT. Let me place for this. If we rewrite this with BT, if we replace BT by WT minus this one, which we can do, we just have defined WT like this. We don't know yet which process we have to take. Then dxt equals mu minus rxt dt plus sigma xt dwt minus, we take sigma xt alpha s dt. That's the same. We just have add and subtract alpha s. The integral 0 t alpha s ds. Okay? Okay. And that's because, put it like this, that's, if you like, a strong solution, but nevertheless, so that's kind of just we have a new function of t. We have defined wt, a new function of t, our old function. It's for each wt for each omega. We have defined, put it like this. Wt is a new random function, so it depends on the underlying probability omega. But each scenario, we have taken our bt of omega minus. I want to say that's just an operation on the space of functions. Okay, so it's deterministic. And we write this integral equation, which in such a sense that we now replace bt by wt and alpha. Okay. But
Okay,
we
sir.
want now to, yes, please.
No, sir. No, sir.
Yeah. So now we have put in somewhere here our alpha, which we want to use for the new measure. We want now to define a new measure, under which we know under the new measure Wt will be a martingale. So what we need to know is that this becomes driftless. So this means if you are at this stage, what you want to know under the new measure under Q, this one is a martingale. Wt is martingale. What we need to ensure is that this one is 0. You see it? Stochastic integral with respect to martingales are again martingales, as we have seen in discrete time finance. If assets are discounted, assets are portfolio, are martingales. If discounted assets are martingales, also discounted value processes are martingales. And stochastic analysis means stochastic integrals of martingales are martingales. Okay. Okay, now we see how we have to define alpha S. Huh? Huh? No, for every omega, actually. Because mu minus r divided by sigma. Now you can see how you get in much more general cases, yeah? So it's clear, once you have understand Girsanov transformation and a little bit of stochastic analysis, how your martingale measure looks like. Okay. We have done it here. dxt, we replace we replace dbt by our new wt minus alpha t dt, where we don't know what it is. This last step, we look everything which is with respect to dt, dwt, so we collect stochastic integrals and standard integrals. So the integrator with respect to dt integration is this one, and we collect integrands with respect to stochastic integrator. This one's, and we want to have this one is 0. Okay. Then we have dxt equals sigma xt dwt, and wt, that's now our q again. I'll make it red. Sorry, I'm stuck. WT Brownian motion under, let's call it Q A, this is alpha. No, which is P star. And then we have constructed the Martingale measure. Okay. But anyway, we knew it, of course, with the return of a riskless asset in an arbitrage-free way shouldn't be higher than the one. Well, that's if you see also the intuitive, an intuitive understanding of markets. That's what's called, so in real life, this should be larger than 0, and then that's called the market price of risk. And that's somehow the difference between real world drift, your return you make on a risky asset, it's mu, and how much you earn more than in the riskless rate compared to the sigma. This means this should be more or less the same. Independent of mu and sigma. So that's your excess return per risk unit for the bankers among you. Excess return per risk. Okay, now first the theorem. So we will end this lecture with this theorem then. Let's take this density here. Now alpha is mu minus RS. And then we define that the density, and we define the new measure P star be the probability measure given by with this density. Then the discounted price process is the P star Martingale. P star, that's our, in this case, unique Martingale measure. So what we know already, Black-Scholes market is arbitrage-free and complete. We don't know it because we haven't proved it. We have just proved it in discrete time. Actually, we have only proven it for discrete time and finite state space. But meanwhile, I think you believe that's valid in any market. Uniqueness of equivalent martingale measures gives you completeness. Nevertheless, we will prove your completeness without restoring to a fundamental theorem, because the fundamental theorem, I told you, you need this functional analysis, this duality, like Hahn-Banach theorem and so on. But for the Black-Scholes form, for the Black-Scholes market, you can actually prove directly that this one is complete without restoring to the abstract fundamental theorem of asset pricing, which I just cited. I proved it for one point in time, finitely many states. Is finitely many point in times, finitely many states, omegas, then you can do linear algebra, as I try to explain to you. But of course, the same is true, not of course, but it's true. And that's one of the few papers on mathematical finance which get into a real mathematical journal telling you that the fundamental theorem for asset pricing is valid for all what's called semi-martingales, for a large class of processes, in particular for the Black-Scholes model. But because we don't go more into detail in the general non-arbitrage theory, we'll just prove that the Black-Scholes model is unique, that you can replicate everything. And because here we use what's called the Martingale representation theorem for Brownian motions. So in a Brownian filtration, if something is driven by Brownian motion, every other martingale is a stochastic integral with respect to Brownian motion. That's a deep insight of stochastic analysis, independent from the fundamental theorem of asset pricing. So this we will do in the next lecture.
Yes, sir.
Yeah?
Yeah, yeah.
Okay,
So,
thank you for your attention.
yeah, thank you so much, sir, for this wonderful lecture. I hope all of us are benefited from this. Now we are taking a break of 1.5 hours. So we will start again at Indian time 2:30.